in there. Thank you very much.
Yes, we're very happy to have Gleb Aminov to tell us about what languages do black holes speak.
Yeah, thank you very much. Thank you for giving me the opportunity to speak here. So yeah, my talk is about the quasi-normal modes of black holes, or another term is a language I use today. So we'll start with answering the question, why are we interested in quasi-normal modes from the physics point of view, and like current and future experiments. Then we'll give a broad definition of what is a quasi-normal mode is, because there's very different backgrounds, black hole types, and so quasi-normal modes in that sense, they're not really different from normal modes. And then we'll move on to introduce two analytic approaches. So basically, most of the time people use numerical methods to compute quasi-normal modes, and so our main goal here is to close the gap between numerical and theoretical approaches, so that to do this as analytically as possible. And in some cases we really have, I would say, fully analytical description for them, and in some cases we're still working on. And finally, we'll summarize the results, what languages and what basically words we discovered during this project. So my talk today is based on two joint works with Albagrassi Hatsuda, first one, second one with also with Paolo Arnaudo Bonelli and Tanzini. And the third work is still work in progress with a PhD student, Paolo. And below you can also see the links to the pages I used some materials from for the presentation, pictures and stuff like that. So let's first start talking about experiments. Why are we interested? So currently we have three ongoing physical experiments that measure gravitational waves. That is advanced LIGO, Virgo interferometer, and Kagura, Kamioki Gravitational Wave Observatory or detector. And all of them are large-scale Michelson interferometers. And like for advanced LIGO, each arm is like 4 kilometers long, and for the others, each arm is like 3 kilometers long. And so what they measure here, you can see here the reconstructed template signal. This is probably more like refined, not exactly the one that they measured, but this is like the main picture they use. And then there is a comparison to numerical relativity. So this is just a result of numerical simulations of Einstein equations. And you can see that roughly we can split the signal coming from, in this particular case, merging of two black holes into three phases. And by the way, this is the measurement made in September 14, 2015, supposedly the first observation of gravitational wave. And so three phases here. They in spiral when the two bodies, not necessarily black holes, can be rotating around each other, and then they will start merging, and finally when the black hole is formed, the excess gravitational energy can be released through ringing. Basically the black hole will emit gravitational waves in this case, and of course they're damped according to the in agreement with the no-hair theorems. This black hole will emit damped oscillations. And so this third phase is dominated by this quasi-normal modes, which we want to study. And so currently there is, like, you could say, debatable topic, but currently there is no agreement on that the already existing measurements can distinguish between different quasi-normal modes that contribute to the ring down phase, because obviously the main signal could be a fundamental mode and there is some mixture of overtones, and so that's a debatable question. Basically, I think there's only one group that says that they can really distinguish them, but most of the community, I think, is not on the same page with that. So future experiments also provide opportunity to measure other kinds of black hole mergers by increasing, like dramatically increasing the arms of the interferometers and basically putting 3 satellites into space on the heliocentric Earth-like orbit, where each arm is like 2.5 million kilometers, and the 2 satellites act like mirrors, and the master satellite here will act as a receiver and transmitter of the waves, of like laser waves. So basically, we are looking forward to this as like 2030s or something. Maybe this will give us better results, or maybe we will figure out how to better analyze the existing experiments, how to better analyze the signal to distinguish different modes there. So this brings us to the definition. What is a quasi-normal mode, like in general, without specifics first? It's very easy. We have a second-order ordinary differential equation. Later I will talk more about how you get there, because you start with Einstein equation, which is not an ODE, but by separating the variables and doing simplifying equations, you basically get an ODE. And the second part of it is that you need to apply certain boundary conditions. So without the same as you would have string modes, right? You will apply Dirichlet or Neumann boundary conditions. You would have normal modes. The same thing happens here. You apply boundary conditions at 2 points, and you expect to have and you actually, for black holes, you will have a discrete set of modes. So yeah, here the main point is that there's 2 parts. You have an equation and you have a boundary condition. So, and there's obviously like many different black holes in different backgrounds. So, and today we're going to focus on mainly on the Schwarzschild 4-dimensional black holes. Even though our methods also are applicable to Kerr cases, and we do that for the to keep things more simple, we'll just talk about Schwarzschild case, and this is basically captures most of whatever happening there. And so for ordinary black holes is like in the ordinary in the sense of pure Schwarzschild solution. The ordinary differential equation is called Reggie-Wheeler differential, or Reggie-Wheeler equation. It's basically when we perturb the Einstein-Hilbert action, and we can perturb it with basically three different perturbations, meaning we can add scalar field to the Schwarzschild solution and solve the equation in the linear, like do the linear perturbation theory in this scalar field, or add electromagnetic, or add gravitational. So there's like 3 different things that we can add. At least that's what Reggie and Wheeler did, and they figured out that all of these 3 cases, even though you start at very different actions because you add very different fields, they're all these 3 cases are described in terms of the same ODE, and then there is additional quantum number here hidden. So f of r is the standard function for the Schwarzschild solution. There m is the mass of the, and g, we put g to 1, so that's why there's no Newton constant here. And this effective potential v of r can be written in terms of f of r and angular number, and this s here, which, as I was mentioning before, I think this is the right thing to write here. Yes. So s for scalar, if you add scalar perturbation, s is 0. If you add electromagnetic, s is 1, and if you add gravitational, s is 2. So
sorry, can you just slow down?
Yeah.
Can you back up to which question are we asking? Why are you changing? Are you trying to test deviations from GR? What are we doing?
So what are we doing? We're measuring, if we are measuring the gravitational wave signal, the last phase of the signal is when the black hole formed, and there is a small perturbation left over from the merger. And actually, in the case of measurements, this would be gravitational perturbation. So this will be, before it formed, there was a lot of gravitational stuff happening, so there is small gravitational perturbation around the newly formed black hole, which will emit things. And so
because the collapse was not started with symmetric and there's stuff ringing down.
stuff ringing down, and this is really similar to adding small gravitational perturbation on top of the Schwarzschild solution. And so what we expect to see
Is it similar or is it the same?
should be the same. So what we expect to see is a combination of fundamental and overtone frequencies from the normal like problem where if you have just a black hole, you would say, oh, what are the quasi-normal mode frequencies? So it's a property of like a string. If you touch the string, it's going to ring at some frequencies. If you touch it too hard, there's going to be overtones in it, right? So the same thing here. It's a property of the black hole, but when we measure in the final phase, the waves are determined by this only the properties of black hole and the perturbation that you have around it. So that's why we went through from the physical signal that we obtain, and we expect to see their quasi-normal modes that are just basically properties of a black hole solution plus small perturbation. And depending on the type of the perturbation, you have different equation basically. But the nice things about Reggie-Wheeler equation is that all three types are basically just encoded in this, let's say, quantum number S. Yeah, it's a classical GR. It's just classical GR, yeah.
Is it basically just like radial part of some wave equation in Schwarzschild background or something?
Yeah, that's what I'm saying. So that's what the next step here. What is phi of r? So you have, let's say you added a small, it could have been scalar, vector, or some part of the thing. It depends on r and t, and you do spherical harmonics, right? And then you write this big radial part, the time-dependent one, and obviously YLMs. So for Schwarzschild, it's spherical symmetric solution, so there's no m in this equation, in this potential, because it's spherically symmetric, but there is L. And so phi of RT, we separate into the exponential dependence on time and frequency, and this function small phi of r here. This is a big phi. So that's how that's what it is. Small phi of r is. It's this part of a radial perturbation of your initial small perturbation. Can I do this? Sorry. Yes, Kerr is very similar, except that you'll have two ODEs. So you would have one ODE describing the angular part that is not trivial, as in this case, not just spherical harmonics, and there is going to be a radial part. So the radial part is going to be very similar to this one. And then you need to solve both and substitute solution of the one into the second one. So it's a little bit more complicated, but the same idea. Now let's see, the second part is always the boundary condition. And so let's see whether we have how do we even apply the boundary condition. For that, we have two boundaries, basically at the horizon. This is the classical GR. So we have r equals 2m, which is the horizon, and we have r goes to infinity, which is infinity. So the two boundary conditions that will create quasi-normal modes are the ones that, yeah, before that we need to see what are we even talking about. So when r goes to at the horizon, obviously v of r is 0, right? Because of f goes to 0. And also when r goes to infinity, v of r is also 0 because of the 1 over r squared and r cubed terms. So above this boundary points, the effective potential is 0, and basically the solution phi is just a plane wave in tortoise coordinate, which is just defined by this 1 over f. So in the tortoise coordinate, near the horizon and near infinity, this is a plane wave. And the boundary condition is basically saying that near the horizon we only have ingoing or infalling in falling waves, nothing comes out of the horizon, and at infinity, only outgoing waves. So no energy influx. So basically the system is closed, there is only small perturbation around black hole, and it escapes through the infinity, the wave, and it falls into the horizon. So obviously we are losing energy, and so the wave is actually damped oscillation, because omega will have what is it real? No, we'll have imaginary part, and to be in agreement with no-hair theorem, obviously this imaginary part has to have a specific sign, so that our black hole is stable. And this is what will happen. We'll have the correct imaginary part of omega, so that oscillations are damped. They are damped in time, though, right? So we can see here the solution we wrote minus I omega t, and now it's like going to be plus minus I omega r star. So for example, if we are looking at the solution that goes to infinity, this is going to be like this, right? So you can only have this solution damped in time, which will correspond to stable solution, but then it grows with r star or r. So that's why you can probably even measure those, because yeah, the amplitude is actually grows with r, but it damped with in time. So next to the black hole, it dies off. Okay, so this is the more general definition, and the main idea here for us will be that this is very similar to quantum mechanics. It's just do you see here, right? If I can write here. So basically, we have a dies off with time, because they have I omega t minus r star here. So it can either, so if omega, omega is like a plus ib, right? Or let's say I.
So you want omega to have the imaginary part of omega to be positive.
Yeah, and b, yeah, like negative. So, but you cannot have both. It's gonna grow either in t or in r, because due to this sign at infinity. So that's also the case why we can even measure those, right? If it would be exponentially suppressed by r, it's already very small, the gravity, and if it would be also exponentially suppressed at large distances, you would never see it. Shouldn't. But it's basically what I'm saying. It's not small. It's not exponentially suppressed in R. But yeah, I'm saying in this solution it cannot be both. You either.
So you say that some other effects happen when R is becoming large. So it grows, like around the horizon it grows, but then it somehow eventually dies. It cannot grow indefinitely at R equal, right?
Well, but the answer is probably is that it's not a real plane wave that we see. It's not always everywhere. So you have like a Gaussian. That's the answer actually. You have a Gaussian packet that moves. We don't really measure plane waves that exist everywhere, right? They're localized. So, but that's a small argument why we can't even see them, because this part in our star is. If you ask for the stability of the black hole, you immediately get growing in R amplitude. So yeah, and the very simple basic idea is that this all looks exactly similar to quantum mechanical problems, where we normally have some kind of well or a infinite or finite well or a step functions, where we separate the region into different, we will separate like X, for example, here, space into different regions, and we solve for the wave function in different regions, and we require that the solution, the wave function is and its derivative are continuous across the whole x line here. So, and this is the first approach that you can, the main observation is that the ODE itself that we wrote for the, on the black hole side is the same as the one that you would have in the quantum Seiberg-Witten curve, or just in this spectral problem where you just act with a stationary, it's a stationary Schrödinger equation. You act with a Hamiltonian on a wave function, and you get the energy times the wave function. The dictionary is that we change the wave function, we change parameters with certain dictionary, and basically it turns out that the ordinary differential equations for ODE for the Schwarzschild is the same as the ODE for the NF equals 3 Hamiltonian, which we can write down. I can write it down here. For some of you, it might be familiar, definitely for Igor. So this is going to be standard p-squared term, and then the interaction is this lambda bar, which is related to the cutoff in the Super-Yang-Mills theory. Yeah, this one I focus mostly on n equals to 3 or greater, but also can be for n equals 2. It just can be a different distribution of masses here. Yeah.
Sorry, naive question, like, why do you need to do this Seiberg-Witten stuff? You can simply, why numerics don't work, or do they work? Like just numerical solution of Schrödinger.
So numerical, you'll get just numerical numbers by solving and expanding like z variable. Basically, you'll the thing here is that we'll talk about it a little bit more later, is that you can't solve for the wave function continuously in the whole region, basically, in z. So I mean, you can numerical approaches, you'll expand in like a variable, like a z variable, and you write your solution up to some order in z variable, for example, here. And this will not give you analytic results, and you'll just get like, you'll be getting continuous fractions, for example.
So you want dependence on the parameters?
Yes. So I want dependence on the parameters. In the Schwarzschild case, it's a little bit more complicated because there's no any other parameters except for the frequency itself. But in the de Sitter and anti-de Sitter case, there is additional parameter, which is you add lambda, cosmological constant, and then you can fix it, and you're left with additional parameter, which is the radius of black hole. And so you can expand in the radius of black hole. So basically, if you want an analytic approach, you need to somehow solve your equations, keeping the parameter, and in all orders in the variable z. Not solving like you would do a differential equation, solve it as a trigonometric function, for example, right? You solve just up to certain orders in the variable. Okay, so but the second part is that there is also boundary conditions. And it turns out that in the Schwarzschild case, we are lucky, and those are the same boundary conditions. And sometimes, for example, in ADS4 case, where you embed the Schwarzschild solution in the ADS4 case, those turns out to be boundary conditions on the side of the Seiberg-Witten curve, and boundary conditions on the black hole side are different. And there is a reason for that. I will explain later. So, yeah, x is basically some kind of e to the x is some kind of z here. So this is going to be like, instead of e to the x, you'll have z. Yeah, this is free to find. Yeah, this is you can distribute. This is the symmetry, right? In the Seiberg-Witten curve, you can distribute these factors between. Yeah. Sorry. Yeah. I mean, if this is particularly for an f greater or equal to 3. For n f equals 2, we can distribute them evenly, like 1 and 2. So that's why this opens up the opportunity to use Zyber-Gritten theory, and in particular the A and B periods, right? The A period is an integral around the A period of the curve, and the main tool here is the Nekrasov-Shatashvili function that we say that its first derivative with respect to A is the B period. Yeah?
I'm very confused what just happened. So it seemed like you wrote down as 52, and then you said, I noticed that this also appeared as Zyber-Gritten.
It's the same equation, yes.
So does that mean that the differential equation that we wrote down for my understanding is where a curve comes up is it's like you have the potentials algebraic and you're facing complex numbers.
Yeah, it's an analytic continuation. You can look at this complex. There's going to be variable z here. It's a complex thing, and I will show pictures where you'll see that actual gravitational problem is a real slice. Sometimes it's a line, sometimes it's a circle. So the real gravitational problem lives on a real slice of a complex z-plane.
And the other thing is the Hamiltonian you wrote down just doesn't really look to me at all like the one you wrote down, like the second order you wrote down. Is that just you just expand it out and
No, so you replace e to the x with z variable, and then it will be you'll have polynomial coefficients here or rational functions in z, and it's basically the main thing that you want to look when you compare equations are singularities. So basically there's in this case there are 2 regular singularities and 1 irregular singularity in the Zyber-Gritten equation and in the black hole problem. And so that's where to see this, to figure this out more systematically, first you look at the singularities that actually define the solutions and define the problem. What are the singularities? And first you see that the singularities are the same, and then you can figure out what is the wave function transformation and the dictionary connecting the two. So that's just a matter of changing the variables, and that's it. So that's why I'm not writing too much here, because it's going to be just a dictionary. We all know such dictionaries exist. It's like AGT or whatever. You can rewrite problem in a different set of variables. So, and the main idea here is that there is a B period, and there is a B period quantization, which basically says if you have a quasi-classical, if you look at this from the point of view of quasi-classical limit, there's a turning points in the potential, basically V, sorry. And then there is a turning points where V of R or V of X in this case equals the energy. And there's the particle, the wave here, wave function has the oscillations, undergoes oscillations between the turning points, and then there is it goes exponentially suppressed beyond the turning points. And so basically the B period says that the phase acquired by the particle moving around one period of oscillations inside the potential should be 2 pi I. Or in other words, it's equivalent to saying that the wave function and its derivative are continuous. So basically if you divide the space into 2 parts, the B period quantization here will be equivalent to saying that the wave function and its first derivative are continuous. It's just reformulating that statement. And so this works for the Schwarzschild case, and we'll discuss other cases when it doesn't work too. And so this quantization here, how do it translates into this quasi-normal mode problem? So we wrote that this condition here, and then the B period is actually the second derivative of the Nekrasov-Shatashvili function with respect to A. And now you need to connect this whole thing to the black hole problem. So you can do this by inverting the Maton relation. And so basically you have a dictionary that says here exactly that the energy in your quantum curve is related to this quantum numbers in black hole side of things times this mass times omega part. So the energy is related to the frequency. Omega is the frequency in the black hole theory. And so you need to write, to really use this, equation here, you need to invert the Maton relation and write A as a function of omega. A as a function of omega and other stuff, and cut off lambda. And so by doing that, you can solve the quantization condition to obtain the same n will give you the same n will give you the omega n frequencies. So you can either calculate an from the quantization conditions, and this will determine omega n, which will give us discrete spectrum for the frequencies in the black hole part. And for example, here, this is how the with certain parameters. Yeah.
Can you go back?
Yep.
It's just the back.
Sorry. This is so the B period depends. The B period. We know that what is the Nekrasov-Shatashvili, right, thing. It depends. It's a certain function that depends on the masses. We fix h bar to 1 here everywhere. Right? We know the function. It has a perturbative part, logarithms, and it has instantons. And it's written in terms of A, masses, and so on.
So you're saying in semi-classical limit, the energy of the Schrodinger problem is related to
The frequency here.
It's the usual thing, just the eigenvalues are like derivative of effective potential.
Well, yeah. This part is usual, but this thing, the question is, so your discrete energy levels in the Seiberg-Witten can be connected to the discrete frequencies in the black hole problem. But there's certain things here that we have to deal with. That we have A, which is going to be a very complicated function of everything else. A is a complicated function of energy, which is sometimes also notation used like small lambda, which is a thing that enters the Schrodinger equation. So it's a complicated function of all these things. And you need to invert that. So you can do it perturbatively. So, and this is the first thing. And then you substitute this A as a perturbative expansion in lambda into the B period, and now you can perturbatively solve it for the omega n frequencies. And what happens is that you cut off at certain orders of lambda, right? So you substitute A into the B period, and you perturbatively expand up to certain order in lambda, and you cut it like say 3, 8, 12, whatever number of instantons you want to have, and this will give you will give values of the frequency closer and closer to the known numerical computation. So basically, and similar things for Kerr black holes. So this is a short version of what happens here, but here's an interesting question. You can see that in the dictionary, lambda is actually omega. So what I was saying is that I have a perturbative expansion in lambda in the cutoff parameter or instanton parameter, and it's actually in the dictionary, it's just omega. It's nothing else than just omega. And so the natural question is saying, well, then I'm actually expanding for small omega, right? They're the same. I should be actually expanding in small omega. And that's it. Why am I talking about cutoff parameter lambda? And that's another interesting question, is that it's not really the case. So if you try to substitute lambda as omega and re-expand in powers of omega, turns out you won't have nice answers. So this is not a small omega expansion. This is still an expansion in instanton parameter, which is a little bit strange for the black hole theory. And this is because to really expand in omega, we can look here. There's the first instanton correction here has a pole here, right? So it's 4a squared plus 1, 4a squared plus 1, and the leading order for a was 1/2 square root of 8 omega squared minus 1, and plus corrections in lambda. So you can see that 4a squared plus 1 is actually 8 omega squared. And so the first instanton correction is actually of order omega squared. And then we can look further and further. And as these poles in the Nekrasov-Shatashvili function, they grow with the number of instanton, we'll see that this pole will grow at the according rate as grows the lambda, power of lambda, such that every instanton will start with omega squared. So to really get small omega expansion, you have to resum infinitely many instantons. This is just one of the questions. But still, the approach where you don't do the small omega expansion, but you do an instanton expansion, you keep lambda, even though it's the same as omega, you think of it as a different variable, you expanded it, and then after you made an artificial cutoff at this lambda, you only then substitute lambda as omega. So this works in that way.
What it means to black hole? Some different, so it's part of the answer for small omega, or what it is? Do you understand the physical meaning?
This is you artificially create an additional parameter with this instanton, which actually governs the answer. And if you don't have this artificial, you have just omega, you need to do another approach. You need to resum all the instantons, basically.
But what guarantees that you introduce some parameter which is artificial, but then you expand it, and what guarantees that you get anything close to whatever expansion?
So what guarantees it is that instanton, in that sense, the instanton approach is more or less bulletproof because we know it's convergent in lambda. And so this expansion, even though it's artificial, it's convergent. And if it has a radius of convergence, I'm saying. And if you're inside the radius of convergence, you're bound to get good answers.
So in other words, so you invent another parameter, you re-expand your original problem, which was in terms of omega, you get a clever parameter in terms of which is convergent, and that's how you get the expansion.
That's how the instanton part works. Well, but the thing is that still here, we do mostly numerical. So even though you have analytic expressions here, right? So this one on the left will be an analytic expression. But to get these numbers at each order, you're going to solve numerically because it's pretty ugly thing. It's a result of inverting the Maton relation. It's very complicated. So that's. It will have. So inside it will have gamma functions of omega. Yeah. So this is like one way of doing things.
How does this compare to what people who study in
This they didn't know. They didn't do this, and for them it's surprising that it works. Well, it's surprising that. So going back, why this works is that. Two things happened. First, ODE and the boundary conditions agreed on the Zyber-Witten site and black hole.
So you guys solved the same equation.
And with the same boundary condition, this happened. And second, what happened is that we are inside the radius of convergence for some of the lower n numbers. For higher n numbers, we're probably outside. So the thing is, this captures the fundamental frequency and some lower overtones.
Wait, but here, so the last line is the numerical biology.
Yeah, and this is just numerical approach, and this is what you can get with 12 instantons in lambda expansion. Yeah, so pretty good, and but also adding the Pade approximum. So also the fact that you need.
What is NV?
Number of instants. This should be. Yeah, this should be number of instantons. I don't know. I don't remember. This is it was not my notation in the paper, so I don't really remember. But this is just the number of instantons. 3, 8, 12. Yeah. Yeah. So like first you start with one digit as you have 3 instantons, and then you go closer and closer as you add instantons.
So why wouldn't people just do whatever they're doing before? Why didn't they need your help? I think we have already asked, but maybe you can revisit this problem now. I mean, this question now.
So you can answer some other questions about stability with it. If you have analytic techniques, you can answer some other questions and provide some, use it for proofs and stuff like that. And also we'll see it in ADS case with another approach, you actually get better, in some cases you get faster and more precise results than numerics.
But you said something like, if I understood correctly, so here this number doesn't depend really on anything, it's a number.
Yeah.
In some cases you have additional parameters, and the dependence on the parameters, that's what we are with.
Yeah, here you can also expand. So if you expand in small omega, that's another project we're doing. If you're just, your omega can be your parameter. So you can expand as a Taylor expansion in omega, and this will also be pretty good. So here what happens is that the mass of the black hole is always multiplied by the frequency. So your frequency is always some number divided by the mass of the black hole. There is no expansion in the mass of the black hole. In the ADS case, this becomes, the frequency is a Taylor expansion in the parameter, which is the radius or the mass of the black hole.
So if you say that the numerical people, that's what they cannot do at this expression.
Yeah, what they can do in certain cases, and then they don't know how to go to all orders, or actually Yasuki was doing the expansion in a parameter, but his coefficient is in this Taylor expansion, they would be numerical. So he is doing this like semi-analytical approach where he still expands in the parameter, but coefficients are numerical only. And so in the ADS case with the next approach, we'll do fully analytical, we'll get to fully analytical answers. So why we need the second approach, as I said, in some cases, the B period is not actually the whole story, because it's only for specific boundary conditions where you require that the wave function is regular at certain points. And when it happens so that it's not regular at those points, the B period is not enough. You have to add something more. You have to consider the general wave function solution. And so in this case, in the Schwarzschild ADS4 case, you can see that there is 4 singularities, which is like 1, 0, t, and infinity, and t is our instanton parameter. Yes, instanton parameter in the NF equals 4 curve. So the ADS case corresponds to NF equals 4. And so basically, yeah, there is a complexified constant, and this allows us to have Taylor expansions in the parameter. And the boundary conditions are applied obviously at the horizon of the black hole and then spatial infinity. In this case, for example, you can see for t around 0, this is just 2. So it's not at the singular point of the equation, and that's why the B period will be not enough. And so the general idea here is to divide the complex Z-plane into 2 regions and do the basic quantum mechanical approach, where we solve in each region perturbatively in the certain parameter, which we choose, such that, so we have an expansion parameter. In our cases, we'll consider today, this is going to be either T or RH, or 1 over RH. So 1 over RH is a good parameter when you want to talk about ADS CFT, where you're interested in heavy black holes, where small black holes are not really stable from the CFT point of view. So first we'll still do small black holes, because this is a part of the story that relates to the flat case. And so the parameter is chosen such that the leading order solutions are elementary functions, and in the ADS and DS cases, those are just rational functions or a logarithmic function. And so the Wronskian of this leading order solutions is always a rational function. So this is important, because now you can, in each order, you can write down the generic solution that depends only on the previous orders. And so this becomes a what is it? Basically iterative solution, where you just take integrals from the previous orders. And the thing is, when you have the rational function as your Wronskian here, you will always know what is the answer. You don't actually need to take all the integrals. So basically, all the functions that will arise in this expansion are certain functions that are actually multiple polylogarithms, and at order t to the k, only multiple polylogarithms of weight less or equal to k arise. So basically, you can either just reduce the problem to solving the linear equations in constants, because you know all the functions that can appear, or you can just use the recurrence relations where you reduce, by integrating by parts, you reduce the integral at certain order to integrals that you have already taken in the previous order. And so at each order, you know what the answer will look like. It will include the multiple polylogarithms of certain weight. And the weight here is actually the sum of all the indices. So the sum of all the indices is called the weight, and the level is the number of indices you have. So in this case, the level is m. And the main idea here is that it's really easy to take a derivative of this function, and the derivative is if the first index is greater than 1, you just drop 1 over k once, multiply by z, and you just decrease by 1. So z dz acting on this function, it just decreases the weight, the overall weight, by 1, like so. And the other one, if S1 is actually 1, so this is going to be, the derivative is going to be 1 over 1 minus z. So 1 minus z dz of 1, and something else is going to be S2, and so on, Sn of z. So basically, this is like taking integrals of functions like this, right? So we can always take integrals of this form, of these functions, and the basic answer why this is enough is because in each order we just have rational functions multiplying the previous orders, and the rational functions can always be expanded into the poles, and so anything of this form can always be expanded, right, into some powers here, 1 over z to some power, and like L, K, and there is some sums here. You can always expand it in these monomials, and so when this one of these powers are 1, you basically increase the weight, or if there is not 1 over z or not 1 over 1 minus z, you get the same functions of the same weight. So basically, with this approach, you can analytically compute all the omega k's here. So your frequency, as I said before, becomes a Taylor expansion, in this case in RH, in the black hole radius, and each omega k will be at higher k orders, will be written in terms of Euler sums or multiple zeta values. And those also appear in the computation of Feynman diagrams in QCD, because there's like, it's not exact, we don't exactly have the connection, but it's a very similar approach where they rewrite the equations on Feynman diagrams at higher orders in terms of certain iterative integrals. And so the same thing happens there, and so people were studying these multiple zeta values in physics and mathematics for a long time because of that. And so for smaller orders, we can even write, for example, for this fundamental frequency, we have the full dependence on L and S, so it's a fully analytic expansion with analytic coefficients, and you can find on this link, you can find the results, and you can also see that for inside the radius of convergence of this thing, you match the numerical results, and not only that, you have coefficients here, analytic coefficients in each. So in the case of ADS CFT, people were actually computing these expansions and using numerical methods, and so in this case, our method is actually pretty good. It works fast and allows very precise results. So in this case is actually when you can expand in 1 over RH, so for the big black hole. And to illustrate our method, we take, for example, scalar sector of gravitational perturbation in SADS4. And in this case, the small parameter is 1 over Rh. And we actually have 5 regular singularities in this equation. This can also be connected to the equation, some kind of quiver gauge theory, but we are not using this connection. We're just using the same method by solving in 3 regions for the wave function, and then using the continuity condition on the wave function to get the frequencies. So in this case, to increase efficiency, we create 3 regions. And actually, the solutions in this left region and the middle region, the left region is actually a region around infinity, spatial infinity, and the right region is a region that's next to the horizon. And so in these 2 regions, the wave function is just when you do the proper variable transformation, just Laurent polynomials, so it's very easy to compute them. And the functions, solutions in the region near the horizon is actually turns out to be similar function, but at this point it's not in a single variable, but in more variables. And so the difference from the previous case is that we have the product of z variables on top matching to the powers of matching the indices of summation. To simplify things, the only indices here can be ones. So we only encounter here functions like Li11 or Li1 or Li11, 1, 1, 1, and so on. So they're always, the level is equal to the weight because all the indices are just 1 in this case. Also, the things that people were actually computing in this ADS CFT case is the hydrodynamic modes or the low-lying modes. The low-lying modes because the frequency doesn't grow with RH. So RH is 1 over alpha, and so normal frequencies, standard frequencies will grow with RH, but there is a set of low-lying frequencies that they don't grow with RH. And so as the black hole grows and its radius becomes bigger and bigger, the frequency stays constant. It doesn't grow with RH. And so these frequencies are connected to hydrodynamic modes, and you can even take the limit to M2 brane. So that's what people were doing. They were considering an M2 brane and looking at the low-lying modes for this M2 brane in the ADS. This is ADS4 CFT3. And they're looking at this coefficients here in front of the new, let's say this is instead of RH, now the new parameter is this curly Q. Instead of 1 over RH, we have L over RH, and we're taking the double scaling limit with the angular constant going to infinity. So first 3 coefficients are known analytically, but others were not known, and the main reason is that higher coefficients include this what's so-called colored multiple zeta values. So they're not just functions of 1, but this U1, U2, which are third root of unity. So U1, U2 to the 3rd power is 1. So it's just a complex number. And the advantages compared to numerical methods is that as soon as you have analytic expression, you can basically get any precision pretty fast because you wrote everything in terms of this zeta values, and there is like programs and methods that allow you to compute up to very high precision these values. And we were talking to people that are doing this. For example, to get this coefficient or this coefficient, they need like weeks of computer time to get it precise enough. And here, if you have an analytic answer, you just you get it in seconds. You get having an analytic answer, you just substitute the numerical values for zeta values, and you can get like 15. Here we have 15 digits or more. It doesn't really hinder the computation. And so why is this So this was the story about the ADS case and the sitter case. And so the same thing, why is ADS with small RH expansion is interesting to us is that because if you want to go back and compute small omega expansion in the ordinary black hole case, small omega, where you actually resum infinitely many instantons, the question, what do you have? What are the functions that you have in the wave function when you resum these instanton corrections? And it turns out that near the horizon region, so you would have near the horizon region for the ordinary black hole. So there is going to be 0, 1, regular singularity, irregular singularity, and there is going to be one irregular singularity that formed when you took the cosmological constant to 0 limit, and one of the singularities merged with infinity, which was at t, and now it became an irregular singularity. So around the horizon, you actually have the same functions that you had in the ADS case, and near spatial infinity, you'll have a function that has to cover an infinite interval. So, and that's why we have functions that are actually, the solution is written in terms of this multiple polyexponential functions. And the difference is that compared to the multiple polylogarithms, there is a k1 factorial here, which wasn't there before. And this k factorial allows to increase the radius of convergence to infinity, basically. And this is a generalization of exponential integral functions. So there is an exponential integral function that is defined in the way like this. And it goes to 0, obviously, by definition, when it goes to minus infinity. In the same case, the corresponding functions here is called multiple polyexponential integrals, and they also go to 0 as the argument goes to 0. So there's two sets in analogy with this one, where there is another function that you can call it, let's say, E, goes the integral from 0 to z, and it has a this kind of Taylor expansion representation. Those two are related, and the relation includes logarithm and the Euler constant. The same thing here, we'll have two sets of these Taylor expansion functions and the polyexponential integral functions. So that's going to give the answer in the case of the in the flat case. And so to summarize the results, basically we see here that there's like first line where we have words or functions that enter in the flat case. Then the second line, the functions that we expect or we see in the ADS or DS case. And then there's many other cases of black holes where we can also expect many other kind of functions appearing the similar way as iterative integrals. So yeah, that's sort of a summary. Thank you very much for attention. Yeah, any questions? That's an interesting question. Is there a physical region? Why do they coincide? For now, for us, it's it's an observation that the equations have very similar structure, and not only the equations but the boundary conditions turns out to be the same in certain cases. But it's a very interesting question that would be interesting to answer.
But the equations are not that hard. I mean, it can be just a coincidence that like also the boundary conditions are not that.
It can be because there's not that many second-order differential equations with this structure. I mean,
there are a lot of Cyberwind curves like p squared q. Yes. But so the rotating curves are the large class.
Yeah, this is a large class. Yeah, but as I said, like the methods, the second approach, it doesn't require really knowing the the curve, you can just do it perturbatively and get analytic results. The thing is that people weren't, so when the like finer point is that when you can solve, if you can solve for the wave function that covers both boundary conditions, right? There's problems like that where you can solve in the region that is going to cover both points. You have one expansion for the wave function, and it covers both points where you apply boundary conditions. In that case, yes, you can. It's very people would get results, analytic results. But for some reason, and it happens all the time, where you cannot actually solve your radius of convergence is only up to the second point. So you can solve locally in two regions, and then you need to apply the continuity condition. And that, for some reason, wasn't done in the like gravity setting. People weren't using standard quantum mechanical things in gravity. So that's what we were basically doing, because yeah, it wasn't done before.
You have some example of black holes that map to quiver theories, right?
Yeah, it should be. I mean, that's the general agreement that this thing here should be mapped to quiver, where it's just because you have 5 regular singularities, right? And that tells you that it should be a quiver gauge here. And yeah, I don't know, maybe Alba with some other people worked out some examples, but yeah. This one we expect to be a quiver gauge theory. Yeah, thank you very much.